Hi, my name is Kruthik Alapati, and this is my Lab 3 on the trajectory of a star around a black hole. The objective of this lab was to observe the trajectory of a star around a black hole on a glow strip model and use the momentum of the star to determine the mass of the black hole. This can be determined by using Newton's second law and Newton's law of universal gravitation. So here you can see the equations for Newton's second law and Newton's law of universal gravitation. You can see that net force is equal to the rate of change of momentum, which is equal to the parallel component of the rate of change of momentum plus the perpendicular component of the rate of change of momentum. And you can see the parallel component of net force is equal to the rate of change of the magnitude of the momentum times the direction of the momentum. And then you can see the perpendicular component of net force is equal to the change in direction of the momentum times the magnitude of the momentum. And for Newton's law of universal gravitation, you can see that the magnitude of the net force is equal to the magnitude of the gravitational force. And here's the equation for the gravitational force, the magnitude of the gravitational force. And I rearranged that to get the mass of the black hole right here, which I'll later use in my glow script model. So here's my glow script code for the model for the trajectory of a star around a black hole. For the seed, I use my email to create a unique seed for the trajectory. You can see the gravitational constant, the mass of the star, and the time interval, which is 86,400 seconds or 1 day. So this is the second part of my glow script code, and this is the calculation loop for the net force. And in order to find net force, I had to first find the change in momentum over the change in time. And in order to do so, I first had to find P initial and P final, and I did that by multiplying the mass of the star by the initial velocity and the final velocity. And then I found the change in momentum by subtracting the final momentum and the initial momentum, which you can see right here. And then I found dp dt by dividing the change of momentum by the time interval, and then I set dp dt equal to net force. So I found the parallel component of the change of momentum by using the formula earlier, which is the change in magnitude times the direction of the momentum. And then I set that equal to the parallel component of the net force. And then I found the perpendicular component by subtracting the parallel component of the rate of change of the momentum from the overall rate of change of momentum. And then I set the perpendicular component of the rate of change of momentum equal to the perpendicular component of net force. And then I used the rearranged equation for the mass of the black hole that I showed you earlier to find the mass of the black hole, and then it's printed. And you can see the code on the right, which prints out the net force, the parallel component of the net force, and the perpendicular component of the net force. So here's my model for the trajectory of the star around the black hole. And you can see here that the parallel component of the net force is shown in purple, the perpendicular component is shown in blue, and the overall net force is shown in orange. And on the right, you can see that the code printed out the mass of the black hole, the overall net force, the parallel component of the net force, and the perpendicular component of the net force. And the mass of the black hole is calculated to be 8.174 times 10 to the 33rd kilograms. So what does it mean? In your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So since net force is equivalent to the rate of change of the momentum, the rate of change of the parallel and perpendicular components of momentum will be equal to the parallel and perpendicular components of net force. The components of the rate of change of momentum and the components of the net force are not different. What if? Imagine the black hole whose mass you found was removed and a different black hole is placed in the same location. Assume the motion of the observed star remains unchanged and is only affected by the gravitational force of the new black hole. Could you tell the difference? In other words, is it possible for you to find the mass of the new black hole that is different from the mass you found for the original one? So my answer for this was that since the gravitational force of the black hole is determined by the distance between the star and the black hole and the masses of the star and the black hole, if the motion of the star remains the same, you would not be able to tell the difference between the old black hole and the new black hole. This is because the trajectory will only change if either the mass of the star or black hole or the starting position of the star were to change.